In this video, we're going to be talking also about data analysis, but here we're going to be talking about not fitting of the peaks, but what do we do after we fit the peaks? So how do we find the change in enthalpy associated with breaking a hydrogen bond? So we're going to use what's known as the Van 't Hoff equation, which relates equilibrium constant, usually denoted as a capital K, and temperature, and it's going to use both the change in enthalpy and the change in entropy of reaction in this relationship. And sorry, I think Van 't Hoff is probably misspelled. So the Van 't Hoff equation is the natural log of K, where remember K is our equilibrium constant, is equal to negative delta H divided by R times 1 over the temperature plus delta S divided by R. Remember that equilibrium constant is defined as the concentrations of the products divided by the concentrations of the reactants. Usually these are multiplied by each other, and we don't include water or solids. R here is your gas law constant, and here we're going to be using the value of R as 8.314 joules per Kelvin times mole. And so if we were to take our temperature-dependent data and graph the natural log of K divided by the inverse temperature, we'd get that our slope would be equal to negative delta H divided by R, and our y-intercept would be equal to positive delta S divided by R. So we can get both of our delta H and our delta S from this trend line, this linear trend line. So what is our reaction exactly when we're looking at this for the Hofmeister effect project? So in this project, we have a small organic molecule. One of the molecules we're using is methyl acetate, and we can think about having two D2O molecules or deuterated water, or we can think about water if we're not in our deuterated water system. We can think about having two water molecules that are hydrogen bonded to the oxygen on the carbonyl group of methyl acetate. And this is pretty stable to have both of these hydrogen bonds. And if we add heat to this system, we will break one of the hydrogen bonds, forming a single hydrogen bond from one water molecule to methyl acetate, and plus a free water. So we'll have the following reaction. So we can think about here, we're going to have delta H greater than 0. This should be endothermic because we're adding heat in order to break that intermolecular force. And delta S should also be 0 because we're going from one reactant in the solution phase to two products in the solution phase. And so because these are all in the same phase, their entropy should be similar. So if we're going from 1 to 2 free bodies in the same phase, we will have an increase in entropy. So our equilibrium constant K is then equal to the concentration of the one hydrogen bond species divided by the concentration of the two hydrogen bond species, because we want products of reactants and we won't include pure water. And because of Beer's law, we know that that is equal to the absorbance at 1725 approximately inverse centimeters divided by the absorbance at 1705 inverse centimeters.
The summary page has also been updated. This is also, notice, now automatically pulling this when you run Solver. So it's automatically pulling these peak areas. You no longer have to copy paste them in. And there's an equation that relates delta H and delta S with inverse temperature. Or sorry, it relates the equilibrium constant, or this ratio natural log of the peak absorbances. Remember, peak absorbances are directly proportional to concentration at a fixed path length. It relates that equilibrium constant natural log to inverse temperature in Kelvin. And so if we plot that, we can actually get delta H and delta S from the slope and the y-intercept using the gas constant. So that's exactly what this is doing. It's plotting that. We do have a beautiful R squared, so we have a nice linear trend here, and with our slope and our y-intercept are going to give us delta H and delta S. And again, these are already sort of set up to calculate this for you. All you have to do is change your slope value to match, which this doesn't. This looks like it's hasn't been updated. So 1286.5. That might have been because I messed with some things. And 4.5255. Once I plug those numbers in, it'll automatically update. My delta H is 10.7 kilojoules per mole, and my delta S is 37.6 joules per Kelvin per mole. And so when you're analyzing your data, this is going to take a while, even with some of these sort of auto calculating for you. Doing the solver and checking to make sure that solver is doing the right thing is going to take a while, right? You shouldn't, if you ever get a line that has like an R squared on this summary page of like 0.5 or 0.4, you don't have a line. And that probably means that somewhere along the way, your fits in those temperatures are wrong. And so you will want to check the solver analysis page and see what's going on. Right, so I know that was a lot, but hopefully between that and just using this a few times and talking to me about this a few times, we will get someplace with this. I know that was a lot of information. Sorry.